So please take the floor.
Okay. Should I start or we wait for? Okay. Okay. So welcome everyone to the defense of my PhD thesis. I am Anthony Schrapffer, and my thesis was in joint supervision between the Universidad de Buenos Aires and the Institut Polytechnique de Paris. And my presentation of today is about high-resolution numerical analysis of the interaction between land, river, floodplains, and the atmosphere in the La Plata Basin. I will first start with a definition of floodplains. Floodplains are areas that are periodically inundated by the lateral overflow of rivers or lake and or by direct precipitation or groundwater. So basically, there are low slope regions which can get flooded by remote precipitation or local precipitation with a possible interaction of the groundwater. So there are a convergence of water into a low slope area. Large floodplains are principally driven by the overflow of large rivers. You can see here the example of the Paraná near Corrientes, and you can see how the floodplains get flooded by the increase of the river level. Then these large floodplains have a regular annual cycle of flood, which is driven by remote precipitation over large areas. You can see here for the Amazon and the Pantanal, the annual cycle for a century period of the precipitation in blue and the flooded area in red. And you can see how we have a regular pattern of flooded area which is related to the precipitation. Then these areas are difficult to study because there are extensive regions with scarce observations. This is why we need modeling and satellite data. Concerning modeling, the climate models usually don't include the floodplains. So we have large open water surfaces which are not included in these models. And this is more important for tropical floodplains because over these regions there is more energy available. You can see here some example of the large tropical floodplains in the world. And also floodplains are rich ecosystems because they have high biodiversity, because they are aquatic terrestrial transition zone, and they also exchange nutrient and biota with the river system. They also provide the nitrification of the water, carbon sequestration, and as we are in flooded area, we are in anaerobic conditions. So wetlands are the world's first methane emitter. Finally, for human activities, we have agriculture and cattle, river transport, fishery and tourism. However, they are threatened by land use changes, channelization, excessive fishery, climate change and wildfire. So, observations and modeling of large tropical floodplains help to predict the evolution of these fragile ecosystems faced to climate change and land use changes. This thesis aims to study the floodplains with a focus on water resources. The region of study is the Pantanal, which is one of the world's largest floodplains, and it contains an original study coupling the floodplains with the atmosphere. Our two main scientific questions are: first, how to represent large floodplains at high resolution in land surface model, and how does the floodplains interact with land and the atmosphere over the Pantanal. This is the outline of this presentation. I will first start with a general introduction, then next section is about water cycle and its exposure to the atmosphere. I will then introduce you to the high-resolution floodplain scheme I developed during my thesis, and we will focus on floodplains atmosphere interactions before giving some perspectives to this work. First, the introduction. So, South America is a continent of floodplains because we have extremely flat area and very high precipitation. So this leads to a dense river network and to the presence of many floodplains that you can see illustrated here. And the Pantanal is the floodplain which is inside the blue circle. The Pantanal is in the upper Paraguay River Basin, which is delimited here with a black line, and it's surrounded by the Gran Chaco Plains and by the Cerrado Mountains. It's a semi-arid region, and all these basins have the same annual cycle of precipitation, with a wet season between December and February, and a dry season between June and August. And you can see that we have the highest precipitation in the Cerrado, and the precipitation decreases towards southwest in the Gran Chaco. And therefore, the hydrology of the Pantanal is mainly driven by the precipitation on the Cerrado region during the wet season. And this is why I will make a particular focus on this wet season along the presentation. So to first give you some understanding of the wet season in South America, we'll tell you about the South American monsoon. Here you can see the upper Paraguay River Basin and the La Plata Basin. So first we have trade winds bringing moist air to the continent from the northeast. Then you have a moisture accumulation over the Amazon with high precipitation. We have a recycling of evapotranspiration that feeds the atmospheric moisture. And this moisture flow is deflected by the Andes to the south, and it's carried by a climate features which is called the South American low-level jet. And this drives the precipitation over the La Plata Basin. So the Pantanal, the South American low-level jet flows over the Pantanal, and the Pantanal is at the transition between the Amazon and the rest of the La Plata Basin. We can now look at the Pantanal hydrology. Here you can see in blue is the precipitation, in green is the flooded area, and in red the discharge at the outflow of the Pantanal. So what you can see that we have the peak of precipitation in December, January. The water then flows to the Pantanal and floods the Pantanal, and a few months later we have the peak of flooded area over the Pantanal, and finally a few months later you have the peak of discharge at the outflow of the Pantanal. So it's a complex hydrological cycle, and the Pantanal acts as a hydrological buffer. Then it's a very flat region, so this leads to a complex river network that you can see illustrated here, and in red you can see the flooded fraction. These flooded areas are important for land-atmosphere interactions. This is why I will give you some basic concepts about this land-atmosphere interactions. Basically, this can be studied using two balances, the energy balance and the water balance. So first, the energy balance is mainly driven by net radiation, which is the income of energy at the surface, and it reflects the shortwave and longwave radiation. Then this energy can be stored into the ground. It can be dissipated through latent heat fluxes, which are related to evapotranspiration, or by sensible heat fluxes, which is driven by the difference of temperature between the surface and the first meter of the atmosphere. Then you have the water balance, which is, so you have the income of water from the precipitation. Then the water can infiltrate, it can evapotranspirate, which can be by direct evaporation, transpiration, which is the evaporation through plants, or you can also have the evaporation of the water on the canopy. Then this water can be laterally transported by runoff and groundwater runoff. So now the question is, what happens with a flooded surface? Here I show you what can happen with some very basic assumptions, so you can have an idea of it. So first we will have more water at the surface and in the soil. So we will have an increase of evaporation and transpiration. We have this increase of evapotranspiration, and therefore we have an increase of latent heat fluxes. And this is why we have a redistribution of the fluxes at the surface, and we will have more latent heat fluxes and less sensible heat fluxes. The shortwave and longwave radiation can also be affected, and we may have an increase of the net radiation, because water absorbs more energy at the surface, and also we have lower temperatures, so we will have lower long-wave emission at the surface. Concerning hydrological modeling, I show you there are two families of large-scale models to simulate the hydrology and the floodplains: the global hydrological models and the land surface models. Global hydrological models are more used by hydrologists, and they focus on the transport of water, while land surface models are used by climatologists and focus on the interaction with the atmosphere. Global hydrological models have a more complex river and floodplains modeling, while land surface models have a more complex land surface processes. And global hydrological model need a more important calibration, while land surface model need a longer time to initialize the simulation, a larger spinner. Here I show you two examples. So for the global hydrological models, this is Kama flood. So basically we have a volume of water in our river, and this volume is converted into a river level and a flooded surface using the floodplain elevation profile. And then the discharge is estimated with a Savenant equation using the river level. For the ORCHIDEE model, we have different reservoirs for the different processes, one for the river, one for the drainage, and one for the runoff. And then for the floodplains, we have an additional reservoir which is able to receive precipitation, to evaporate, and to infiltrate. Here the river discharge is estimated in a more simple way using simplification of the Manning equation. And so we have a direct relationship between discharge and the volume of the different reservoirs. So floodplains are at the crossroad of these two disciplines. Land surface model have a coarse resolution compared to global hydrological model. You can see here is the ORCHIDEE 0.5 degrees resolution compared to the Kama flood vector based grid. And this is why land surface models need a higher resolution to simulate the floodplains. The ORCHIDEE model routing is now available at higher resolution. I've been part of this work, and this is part of my thesis, but this won't be included in this presentation. But from this, we are able to construct a higher resolution floodplain scheme for the model. And one last point is that the common difficulty for both disciplines is to simulate the lateral expansion of the floodplain. This is one of the major difficulties. So why modeling floodplains at higher resolution? First, because this way we'll have a more precise description of the river network and of the topography, and also this will allow us to integrate them in coupled models. What are the main challenges? first, the complexity of the hydrological processes, because we can have divergent flows, resurgencies, we have the uncertainty of the topography, and there are also some numerical challenges, such as first predict the right amount of water and convert this amount of water into a flooded area. And this flooded area is very important because this is the water which is exposed to the atmosphere. This is why this section is focused on the exposure of this water to the atmosphere, using first a satellite estimate of the flooded area and evaluating their uncertainty, and then using a state-of-the-art land surface model. So, to evaluate the uncertainty of the satellite estimate and also to have them for the rest of the study, I developed 5 different methods to estimate the flooded area based on the same satellite data. So first I use optical satellite data from MODIS, I filter the flooded days, and then computed some spectral indices which highlights the presence of water. Why using spectral indices? It's because in satellite data we have different values for different spectral bands, and the elements of the surface will reflect differently will have different properties, whether if it is water or green vegetation. This is the spectral signature of the different elements. So you can see that combining different spectral bands, we can highlight the presence of water or vegetation. And in this case, all the indices I selected highlight the presence of water. So these 5 different methods are classification methods, because we want to know if a pixel is flooded or not. So I consider 3 of the spectral indices, and I used the first point I used 3 different result methods, which means I used for each one of the indexes, for example here MNDWI, I say okay, for this index higher values corresponds to wetter soil, weather conditions, so I select a result and I say okay, all the values which are higher than this result are flooded pixel and the other don't. So these are the 3 first methods. Then we can use the 3 indexes together to try to capture a more complex data structure using first the Cummins clustering method. So I have my data, I use the Cummins method to obtain 6 different clusters, and then I say okay, the cluster in orange and the cluster in red are cluster corresponding to flooded pixel. And the last one is the principal component analysis method, which is a reduction which allows us to reduce the number of dimensions. So I have 3 indices, 3 dimensions. With the PCA I get 2 dimensions, and then I can apply a result on the dimension which is related to the presence of water. These are the results for these 5 different methods, and what you can see first is that these methods are coherent between them. However, there are some discrepancies even if they are using the same product. You can look, for example, at the NDMI result method, and you can also look at the south of the Pantanal where there are more discrepancies. And if we compare this to the literature, you can see here a study from Padovani, which was also using MODIS but with different methods. You can see that it's coherent with these results, but we also have some differences which are related to the method used. And you can also see water map, and in this case it's also coherent, but water map is only highlighting the presence of deep water. So you just have the main Paraguay River and the lakes along the main Paraguay River. Then we can look at a state of the Then we can look at the result from a state-of-the-art land surface model, ORCHIDEE, which I presented in the introduction. It's another way to estimate flooded area, and it also gives the possibility to access to other surface variables to study the fluxes. I used 40 years offline simulations. Offline simulation or simulation in which the land surface model is forced by some atmospheric conditions. And in this case, I used 6 different atmospheric forcings, and for each one of these forcings, I performed a simulation with floodplains and a simulation without floodplains. If we look first at the discharge at the outflow of the Pantanal, this is a Taylor diagram, so each simulation is a point on the Taylor diagram, and this black point corresponds to the observations, so the closer to the black point, the better is the simulation. What you can see is that the simulation, when we activate the floodplain scheme in the model, we improve the representation of the discharge at the outflow of the Pantanal, which means that we improve the representation of the water cycle over the upper Paraguay River basin. So this is a good point, but if we look at the mean flooded fraction, you can see that, so here is times 2 and here is the best performing forcing, the best performing simulation with floodplains. These are for different periods, but it helps us to give us an idea. What you can see is that first it's coherent because what you can see in dark blue is the main Paraguay River. But what you can see is that it's a very coarse estimate of the flooded area. We don't have the flooded area north of the Pantanal, and we don't capture the complex structure of the flooded area. However, as I said, the simulation may help us to estimate some variables. For example, the evapotranspiration. First, I want to say that there are no perfect estimation of the evapotranspiration to compare the model with. And also, it's difficult to use directly the output of the model because we have first the uncertainty of the precipitation input, of the evapotranspiration formulation, and in this case, these are offline simulations, so we don't have a coupling with the atmosphere. But the good point is that in the model, the water cycle is closed, so we can make a balance over the Pantanal region, and we are using simulation which are over a long period of time, 40 years, so we can neglect the water storage variation. So we have evapotranspiration, which is equal to precipitation minus the discharge. We can correct the discharge with the available observations, and we can also estimate the precipitation uncertainty. What we also have to consider is that the Pantanal is not a closed catchment, so when doing this type of balance, we have also to consider not only the outflow, but also the inflows. And this balance leads to the following results that I can show you in a more friendly way, like this. So what we have basically is that we have evapotranspiration, which is higher than precipitation, which is not common over land. However, it is difficult to conclude because we have high precipitation uncertainty, and we apply this balance to a simulation, to the simulation with floodplains and to the corresponding simulation without floodplains, and this allows us to estimate the evapotranspiration, which is directly related to the presence of floodplains, and we estimated it to 90 millimeters per year. So, first we have satellite data that gives us an estimate of the flooded area. However, there is a large uncertainty depending on the data used and the method used. However, these are very interesting methods, and there are many possible ways to improve them. And concerning modeling, we have seen the importance of floodplains, of the floodplain schemes to correctly simulate the water cycle. It also allows to perform robust water balance over the region, and it avoids underestimation of the precipitation. So numerical modeling and satellite estimate of the flooded area must be seen as complementary tool to study the floodplains. In the next section, I will introduce you to the high-resolution floodplain scheme I developed during my thesis. First, why am I talking about high resolution? It's because now we are using the...
Okay.
Luis, ¿puedes cortar el micrófono? Okay. Gracias. So, high resolution because of the high resolution routing scheme I told you about. So basically, even if we are at the same atmospheric resolution of 0.5 degrees, here you can see the red square is an atmospheric grid point. We are using high resolution digital elevation model data to construct subunits, hydrological unit of this atmospheric grid point. These units are hydrologically coherent, and we can use the high resolution data to better define them. So then, when considering an HTU, first we can we establish the maximal fluidic surface, which is defined from the global lake and wetland database. When we have a maximal fluidic surface higher than 0, then this means that we have floodplains, and in this case, the HTU has an additional reservoir for the floodplains with a certain volume, and this volume and the properties of the HTU, from this volume and the properties of the HTU, we can compute the fluidic surface in the HTU. Here you can see the representation of the HTU with the floodplain. So here you have the floodplains 8, the volume in the floodplains, and the fluided surface. So basically we use two different parameters. First is the flood height at which all the HTU is flooded, and then we have the shape of the floodplain, the beta parameter, which tells us if the floodplains are concave or convex. You can see here an example. This will be like this, the same cut. So here, if beta is higher than 1, then we have a concave shape, and if it's lower than 1, then we have a convex shape. And you can see that the fluided surface, the evolution of the fluided surface depending on the volume and then on the floodplain's height will be different depending on this parameter. So it's a simple way to represent this complex relationship between the volume and the fluided surface. We also have to consider the river dynamic. So first, the lateral expansion of the floodplains is done through the infiltration of the water in the floodplain reservoir into the soil. So you have an HTU that can affect the soil moisture of the whole grid point through infiltration. And then we also have the overflow into upstream HTUs. Here you can see an example. So let's imagine this HTU2, which, for example, may be a very large river. So it has a very large quantity of water in its floodplain reservoir. So you can see that the river 8 is very high. And the overflow is giving to this HTU the possibility to overflow into its upstream HTUs. So you can imagine, for example, the main Paraguay River, which will be the HTUs in yellow, and it's and the overflow allows it to expand the floodplains to the neighborhood HTUs. From this, we perform some simulations using two different forcings, one at high resolution and one at low resolution. A 50-kilometer resolution forcing, which is a reanalysis bias corrected by CRU and GPCC for the precipitation, and a 20-kilometer resolution forcing, which comes from a coupled simulation, in which only the precipitation has been bias corrected by GPCC. For the other variable, we have a dry bias because the precipitation is underestimated in this simulation over the upper Paraguay River basin. So we may have an overestimation of and underestimation of evapotranspiration. And for each one of these four things, I perform a simulation with floodplains and one simulation without floodplains. First, we can look at the river discharge. You can see here in red the discharge in the simulation without floodplains, and in blue the simulation in the discharge in the simulation with floodplains. So what you can see is that activating the floodplain scheme, we improve the correlation of the discharge with the observations. We also have a better mean annual discharge. However, we are still overestimating the annual variability of the discharge. And then looking at the flooded area. So here you can see for the low resolution simulation, high resolution, and compared to GIMS and low resolution routing. So what you can see is that even at low resolution, we now capture the complexity of the flooded area north of the Pantanal. It's also the case at high resolution. You can see that at high resolution, you see in yellow the main Paraguay River, and we are able to expand laterally the flooded area. We just don't capture the central region, flooded region in the Pantanal. It's because it's related to divergent flows, and this is not represented in the model. From this, we can also look at other surface variables, such as the soil moisture. Here you can see the difference between simulation with floodplains and without floodplains, and the soil moisture increased up to 60% in both simulations. And in this case, you can see that at high resolution, we are not able to have the lateral expansion of the floodplains through soil moisture, through the increase of soil moisture. While it's perfectly done at low resolution. So we have more flooded area, we have the increase of soil moisture, so we can now look at the evapotranspirative fluxes. As expected, we have an increase of the evapotranspiration at both resolution when we activate the floodplain scheme. And this is mostly related to the direct evaporation from the floodplains. And if we look at the transpiration, you can see that in the low resolution simulation, we have an increase of transpiration during the dry season compared to the simulation without floodplains. This is an important result because it's the water that flows is able to increase the soil moisture, and then we can have higher transpiration during the dry season. This is not the case of the high resolution simulation, and this can be because first of the dry bias of the atmosphere, so we have a drier atmosphere, and also due to the incapability to expand the floodplains through the increase of soil moisture. So now looking at the energy balance, so we have an increase of evapotranspiration, and therefore we have an increase of latent heat fluxes. If we look at the long wave and short wave net radiation, you can see that there are almost no differences between the simulation with floodplains and without floodplains. So in the balance, you have a redistribution of the fluxes with higher latent heat fluxes and lower sensible heat fluxes. And these lower sensible heat fluxes have an impact on the temperature, so we will have lower temperature over the most fluid part of the Pantanal. That can go that the temperature decrease from 1 to 3 degrees in the most fluid parts. So the floodplain scheme has been adapted to the H2's representation at high resolution, and it is now usable at different resolutions and projections, and in particular for coupled simulation. And this is what this section focuses on the floodplain atmosphere interaction and is based on coupled simulation. First, let me introduce you to the model, the coupled model we use, the regional Earth system model REGI-PSL. So the land component is ORCHIDEE, We are using W or F for the atmosphere and NEMO for the ocean. All these three models are coupled by ORCHIDEE, and the input-output are handled by the XIOS server. And the interaction between the atmosphere and the land components are performed through the planetary boundary layer. We are using different simulations of 20 years periods. We start the analysis at 1998, so 2 years after the beginning of the simulation, so the atmospheric variables can be initialized, and we have 10 years of spin-up for the land surface model. So there are two coupled simulations, one with floodplain, absolute flood, one without floodplains, absolute no flood, and this absolute no flood has been used to force an offline simulation which has the floodplains activity. And this is done to evaluate the impact of coupling on the floodplains plan. First, I show the precipitation. So this section basically focused on the wet season between December and February. So for the precipitation, this is the difference between absolute flood and GPCC, and here for absolute no flood. What you can see is that we are underestimating the precipitation over the upper Paraguay River Basin, and I also looked at other observation of the precipitation, such as CHIRPS and GPM, and basically the uncertainty of the precipitation observation is much lower than the difference with the simulation. So we are underestimating the precipitation. We can also look at it using the annual cycle of precipitation. So you can see this underestimation, and you can also see that the simulation with floodplains has higher precipitation during the wet season compared to the simulation without floodplains. We'll first look at the local impact of the upper Paraguay River Basin. So first on the evapotranspirative fluxes. Here you can see evapotranspiration. In blue is the simulation absolute flood, red is absolute no flood, and the green one is the offline simulation. What you can see is that, okay, activating the floodplains, when we activate the floodplains, we have higher evapotranspiration as expected, and also the offline simulation has much higher evapotranspiration compared to the coupled simulation. And this is mainly related to an overestimation of the potential evaporation. So we are overestimating evapotranspiration when we are not coupling the floodplains with the atmosphere. And then, okay, this difference mainly comes from the direct evaporation from the floodplains, and in this case we don't have any impact or very low impact on the transpiration, and this is because we are underestimating the precipitation, so the vegetation is not able to grow. So we cannot capture this effect on the transpiration. And if we look at the local precipitation, you can see that this is absolute flood minus absolute no flood. You can see that we have a significant increase of the precipitation over the region, and we have a significant decrease over the most flooded part of the Pantanal. And we can understand this from previous studies from Adler and Taylor. So basically we have more moisture over the flooded area. This moisture is transported laterally. However, over the most flooded part, we have downward air movements, which reduce the precipitation locally, while on the surrounding part of the most flooded areas, we have upward air movements, and therefore the precipitation increases here. So this result can be directly connected to these previous studies. And if we now look at the regional impact of the floodplains, First, looking at precipitation, you can see that this significant increase of the precipitation also occurs over the west of the La Plata Basin, and this is also related to the significant increase of specific humidity. Also looking at the regional circulation, and in particular at the South American low-level jet, here I define three longitudinal regions to observe vertical cut of the atmosphere, a vertical cut of the horizontal moisture flux. Here you can see the different region represented, you can see the region with the correspondence of color. So what you can see here is that we have high horizontal moisture flux. This is the low-level jet carrying moisture to the south. And here you can see the difference between absolute flood and absolute no flood. And what you can see is that in region 2 and 3, south of the Pantanal, we have an increase of the horizontal moisture flux on the lower level of the atmosphere between 950 and 800 hectopascal. And this is also true for the green region, the region 1, except around 60 degrees west. And so I looked at it, and this is not related to here we have an increase of specific humidity, but we have an important decrease of the wind of the South American low-level jet, and this produces this reduction of the horizontal moisture flux. So we try to understand the mechanism behind this. So the moisture advection of the South American low-level jet may trigger a positive feedback between soil moisture and precipitation. So here you have the increase of moisture advection, which may increase the moist static energy in the planetary boundary layer. So we have an increase of the energy in the lower level of the atmosphere. This leads to an increase of precipitation. More precipitation also leads to more soil moisture, and as we have seen in the introduction, more soil moisture leads to an increase of the latent heat fluxes compared to the sensible heat fluxes. This leads to a more stable atmosphere in the planetary boundary layer, and therefore we have a decrease of the planetary boundary layer, which at its turn increases the soil moisture. So we have this moisture advection triggering a positive feedback between soil moisture and precipitation. So we have a regional weakening of the region, which is due to the integration of the floodplains in the model. And we can also look at some other regional features, such as the Chaco Low. The Chaco Low is a thermal orographic low pressure that occurs between December and February. It's located in North Argentina and Paraguay. You can see it here with the surface pressure anomaly. And basically, the drier and warmer is the Chaco region, the stronger is the Chaco Low. So if we look at the difference of surface pressure anomaly between both simulations, you can see that the Chaco Low we have a negative anomaly. Here we have an increase of the surface pressure anomaly, so we will have a weaker Chaco Low. And this is logical because we have more precipitation, so we have a wetter and colder Chaco region, so we have a weaker Chaco Low. So finally, we have overestimation of evapotranspiration when in absence of coupling. We have seen the impact of the floodplains on the planetary boundary layer and on the regional and local precipitation. And we have also seen how it can impact other regional climate features. So the main takeaways of this section is that it is crucial to include more surface hydrological processes in regional models. So the overall conclusion of this presentation are that large tropical floodplains in South America have an important impact on land-atmosphere interactions, that satellite data and modeling have their own uncertainties but are complementary tool to study the floodplains, Also, land surface model needs higher resolution representation of the floodplains, and this has been done by using the hydrological transfer unit, the HTUs, and the higher resolution model also improves the spatial representation of the flooded area. We also use this high resolution floodplain scheme in Ecole model, and it has a significant impact on the atmosphere and the precipitation at local and regional scale. And this can also affect the regional climate features such as the charcoal oil precipitation. So I will finish with some perspectives to this thesis work. First, what is the future of the floodplain scheme? First one, very important, is that we need a generalization of this floodplain scheme. So we have to evaluate it over other regions and other large floodplains. We can also improve the surface volume relationship by using, for example, 8 above nearest average or more complex methods, such as it is done in other models. It could also be a good improvement to integrate groundwater runoff. And finally, the model could also integrate other aspects of the floodplain, such as dissolved organic carbon, the carbon cycle, interaction with wildfire, study the impact of climate change and land use changes, and also concerning the corporate simulation to assess the impact of tropical floodplains in high resolution simulation with convection permitting scheme. It could also other improvement can be including other wetland types such as swamps and flooded forests, which are very important in the Amazon basin. Integrate the lake and their surrounding wetlands. The coastal wetlands, which are a bit more complex to represent because they are interacting with the ocean. The deltas, which have the difficulty to be divergent flows, and our model are mainly convergent. And finally, the ponds, which are small lakes directly driven by local precipitation. And the river routing scheme can also go further by with the integration of anthropogenic factors such as dams, irrigation, and the connection between both of them. For example, this dam in Mendoza is actually feeding the vineyards of the region, and also other water withdrawals such as the one related to livestock, domestic and industrial use. So this is the end of this presentation. First, I want to thank you for your attention. I wanted to finish with small poems from Manuel de Barros, which is one of the greatest poets of Mato Grosso, the region where the Pantanal is in Brazil. And I'm open to your questions and comments. Thank you.